Okay, so this is another example. It is a ketone molecule. It has I forgot those two lone pairs. It's a ketone molecule, and now what happens? Again, a two resonance form can be produced for this. If those two electrons, the bonding electrons or the pi electron, just sits on this here, a single bond will be the bond will be broken, double bond, and a single bond will be produced. Okay. And as a result, the carbon will become positive and the nitrogen will become negative. And I have mentioned it many times, so I think that you may understand that what happened. And here, if those electrons just sit on this carbon, what will happen? It will require a negative charge, and oxygen will require a positive charge. So from the previous knowledge, you can very quickly understand and reject this structure, because oxygen has incomplete octet, so this will not contribute. This is out. Now suppose this structure, so-called resonance structure, it has 99% or 99.8% 5% contribution. These are just random values, and it has a 0.5% contribution. Now how the actual structure would look like? As we see that this structure, in this structure the oxygen is neutral, the carbon is neutral, and in this structure it is one positive and that is full one negative. Okay, but this has a very small worth, 0.5%. So how would the actual structure be? Actual structure would again be like this. It will be very much like this, but with some different characteristics. Here again, as you see that the carbon and the oxygen, here the electron cloud will be just like this, that it will give a little bit, very small negativeness to the oxygen and small positiveness to the carbon. Okay, or this is small positive, I have written it very small, maybe you see or you don't see, it is just plus and it's a negative. Okay, so the electron cloud will be arranged like this. Okay, so I can just form it like this, a little bit more toward the oxygen and less toward the carbon. And if you look at this in inductive effect, again the oxygen is more electronegative, so it will pull the electrons inductively toward itself. Okay, so it has more electron density already, the carbon has, and this will have a little bit partial positive charge, because if you are confused, you can go and again watch the inductive effect, so it will be clear to you. Okay, so now here in this structure will have a little bit positive charge, just because of the inductive effect and also because of the resonance effect, because the actual structure will lies between those two. So it has a little bit positive charge and it has a little bit negative charge. So I should not write that here, because no charges, you should not write charges on it, because these resonance structure, just like it will push the electron will be coming here. Okay, and it will form this, and again it will go up and form this thing. This doesn't occur in reality. These things are just to make us understand how the actual structure look like. Okay, so in the actual structure will have more negative oxygen and less negative carbon. Okay, or more positive carbon, because it is a little bit 0.5% is okay contribution, because this is neutral, 0 and 0, but it will make 0.5% extra negative, it will impart 0.5% extra negativeness to this oxygen, and it will take away 0.5% of the electron cloud from this carbon. Okay, so any electrophile, or suppose you have HCl, what will happen? This oxygen will attack it, because it is a little bit negative. It will attack it, and like we discussed in the other example, if you have some nucleophile mean it could be anything. Okay, smiley face. It could be just like you can say sulfur or anything. Okay, so where it will go, suppose you have SH and negative. Okay, where will it go? Suppose it will go to this, attack this carbon. Okay, because this is positive because of two effects. One is the resonance effect and the other is the inductive effect. But this molecule, it is not that much crystal clear as the imide. Okay, so because the inductive effect also play the same role, making this positive, and the resonance is again making this positive. So it is quite difficult to to attribute the reactivity of this molecule just to the resonance, because the contribution of inductive effect is also there. So now let us look at our old friend, this molecule that when we were starting the lectures. So I gave the example of this molecule, that how would it behave. It is not pepperamine and pepperalkene, and right now I think you just may know a little bit, or thing will be now clearing to you. Let's say that it has a contribution of 99.9%, okay, or let's say 99.8% again, because oxygen is pushing electrons, so it has a little, and it has 0.2% contribution. Suppose these are values that are relative values, these are not exact values, but these values are very helpful to make you understand. Then I had just in the previous example I told you that it has 95% contribution and it has 5% contribution. Why? Just because when you go to the rules of resonance, you may know that this nitrogen pushes is a very basic, and it pushes electron, but there is other thing, that oxygen is electronegative, and in the resonance rule we studied that negative charge is happy on the electronegative atom. Okay, so here the negative charge is present on the carbon. It's not more electronegative, but still it has some contribution of 0.2%. Now how would this molecule react? The actual structure of this molecule will tell us that how it will react during a chemical reaction. So it will have like this, CH2, okay, H and H. Now I am writing the actual molecule because it's just electron crowd. Those things doesn't occur. Okay, resonance, it is not occurring. It is just to make us understand. If we are in some illusion that this will go there and this will come here, these are just rules. Some genius people have devised those rules, and those are just to make us understand the chemical reactivity of a molecule. So we should write it like this. So we know that the actual structure, the nitrogen has a lone pair much present on the nitrogen, but the carbon is a little bit negative than normal carbon, and the nitrogen is a little bit has a little bit less electron density than the normal nitrogen. What is normal nitrogen? Suppose this is CH3 and H2. It has, suppose this has 100%, so this has a little bit 99.8 or something. But as now the neutral oxygen here, it is not neutral, it is a little bit negative, and now the basicity for the basicity 2% is very big thing. Okay, 0.2% is again very big thing, because 0.2% can change the basicity or decrease the loss of 2.2% basicity can decrease. The loss of 2% nitrogen or electron cloud of the nitrogen can decrease its basicity by 1,000 times, and just a small negativeness on this carbon can increase the basicity of the carbon 100 or 1,000 times. Okay, so if again you put or place some molecule, some acid here or electrophile, we will be studying those in the reactions. Okay, if you offer some electrophile to this molecule, or HCl, or suppose acid or electrophile, what will happen? Nitrogen is strong base. It will not attack it just because it is in connection with the double bond, and it has lost 0.2% of its electron density. But when you look at the basicity, 0.2% can decrease the basicity of the normal nitrogen thousands of times. So the HCl will be attacked by this carbon. If you want to understand from basic way, so this carbon will attack it, but in reality now HCl will be attacked by this thing. Okay, actually this bond or this electron cloud which is distributed between those will attack the HCl. So how much of the electron cloud here in this molecule has? 2 electrons here, and 0.2% from here is going to make the bond. So that 0.2% shifts to the carbon, and now it will be attacked by HCl. So now the negative thing will attract the HCl, because in HCl, as you know, it is partially positive and it is partially negative because of the inductive effect.